14 billion years ago, something impossible happened. Everything that exists exploded from a point smaller than an atom. But here's what they don't tell you. That explosion might not have been the beginning. Recent discoveries by Nobel Prize winners suggest our universe is just one beat in an eternal rhythm. Before our Big Bang, there might have been another universe, and before that, another. Scientists have found strange heat signatures in space that could be echoes from a cosmos that existed before ours. If you enjoy mind-bending cosmic mysteries, please subscribe. Our journey into pre-existence begins now. Imagine crushing everything in existence into a space smaller than the period at the end of this sentence. All matter, all energy, all of space itself. This is what scientists call the singularity, the point where our universe supposedly began. But there's a massive problem that physicists rarely discuss openly. Mathematics completely falls apart at this moment. When you calculate what happened at the very instant of the Big Bang, the equations return infinity. Temperature becomes infinite. Density becomes infinite. Curvature of space becomes infinite. To a mathematician, infinity is not just a really big number. It's a red flag, screaming that something fundamental has gone wrong with your theory. General relativity, Einstein's masterpiece that describes gravity and the shape of space, works brilliantly almost everywhere in the universe. It predicts black holes. It explains why GPS satellites need time corrections. It tells us how galaxies bend light. But at the singularity, general relativity breaks down completely. The theory that explains everything suddenly explains nothing. This creates what physicists call the singularity problem. If our best theory of gravity cannot describe the most important moment in cosmic history, then we are missing something crucial. Stephen Hawking spent decades wrestling with this puzzle. Roger Penrose won a Nobel Prize, partly for proving that singularities are inevitable in Einstein's theory. Both men eventually concluded something radical. Maybe the singularity never actually existed. Think about what this means. Every atom in your body, every star in the sky, supposedly exploded from a mathematical impossibility. The entire universe emerged from a point where the laws of physics themselves cannot operate. This is not science. This is not even close to an explanation. The problem gets worse when you add quantum mechanics into the mix. Quantum physics describes the behavior of tiny particles, and it has its own set of rules that often contradict general relativity. At the incredibly small scales of the singularity, quantum effects should dominate. But we do not have a working theory that combines quantum mechanics with gravity. We are literally blind to what happened at the most critical instant. Some physicists argue we should just accept the singularity as the beginning of time itself. Before that moment, there was no before. Time started ticking at the bang, but this explanation feels like giving up. It is like a detective finding a crime scene with no footprints leading to it and declaring that the criminal simply appeared from nowhere. Others suggest we need a quantum theory of gravity to see what really happened. And over the past 20 years, several such theories have emerged. These new frameworks reveal something extraordinary. The singularity might be an illusion. Instead of a beginning from nothing, these theories predict something existed before. Our universe might not be the first act in cosmic history. It might be the sequel. What if the Big Bang was not a beginning, but a transition? Roger Penrose is not someone who makes wild claims lightly. At 94 years old, he has spent 7 decades doing mathematics that most people cannot even read. He proved fundamentally the universe is not a one-time event. It goes through infinite cycles. Each cycle begins with what we call a Big Bang and ends in a strange far future state. Then, something remarkable happens. The ending of one cycle becomes the beginning of the next. Our universe is just one chapter in an eternal book. This is not fringe science from an unknown researcher. This is a Nobel laureate saying that everything you learned about cosmic origins might be wrong. Penrose published his full theory in a book titled Cycles of Time in 2010. The scientific community reacted with a mixture of fascination and skepticism. Some called it brilliant, others called it impossible. What makes Penrose's idea different from other speculative theories is that it makes predictions we can actually test. He claims that violent events from the previous universe should have left marks on our universe. Specifically, he looked for unusual patterns in the cosmic microwave background, the faint glow of radiation that fills all of space. This glow is like a baby photo of the universe, showing us what conditions were like 380,000 years after the Big Bang. Penrose and his collaborators analyzed data from satellites that map this radiation. They claimed to find exactly what the theory predicted: circles of abnormal temperature, which they called Hawking points. These points, according to Penrose, are the final evaporations of supermassive black holes from the universe before ours. The radiation from those ancient black holes supposedly survived the transition and appears as hot spots in our sky. Many scientists immediately tried to disprove these claims. Multiple research teams analyzed the same data using different methods. They found that the circles Penrose identified were no more unusual than random fluctuations you would expect from chance. The debate became heated. Papers and counterpapers flew back and forth in scientific journals. Penrose remained undeterred. In 2018, he published new analysis claiming even stronger evidence. He identified hotspots that were significantly hotter than the surrounding regions, far beyond what random chance should produce. The temperature differences were about 10 times larger than the cosmic average. Again, critics argued that similar patterns appeared in simulated universes where no previous cosmos existed. The controversy continues today. Penrose's reputation means his ideas cannot be ignored, but the evidence remains disputed. What is clear is this: a brilliant mind has looked at the universe and seen something others missed. Whether he is right or wrong, his theory opened a door that many thought was permanently sealed, the door to what existed before. To understand how one universe could become another, you need to grasp a strange property of space and time. Penrose built his entire theory on something called conformal geometry. This is a branch of mathematics that studies shapes and distances. But with a twist, it focuses on angles and light paths, while ignoring absolute sizes. Here is why that matters for cosmology. Imagine the universe in the distant future, trillions upon trillions of years from now. All stars have burned out. All matter has decayed or fallen into black holes. Those black holes themselves have evaporated through a quantum process called Hawking radiation. What remains is nearly empty space filled only with photons, particles of light, racing away from each other as the universe expands. In this remote future, nothing has mass anymore. Everything that could decay has decayed. The universe is cold, dark, and consists almost entirely of radiation spreading through expanding space. This is where Penrose saw something profound. Particles with mass experience time. They age. They have internal clocks. But massless particles like photons do not experience time in the same way. For a photon, the journey from one end of the universe to another happens instantly from its own perspective. When the universe reaches this state of pure radiation with no massive particles, something bizarre becomes possible. The concept of size becomes meaningless. If you have no rulers made of atoms, no clocks made of matter, no reference points with mass, then you cannot measure distances or duration. The universe effectively loses track of its own scale. Penrose realized you could take this far future universe and mathematically transform it. Using conformal geometry, you can rescale it so the infinite expanse of the dying universe becomes the infinitely small point of a new Big Bang. The ending and the beginning are the same event, viewed from different perspectives. It is like looking at two sides of the same coin. This transformation is not arbitrary. It preserves the geometry that matters for light and radiation. The paths photons take in the old universe become the paths photons take in the new one. Information encoded in light could theoretically survive the transition. The new universe does not start from nothing. It inherits structure from its predecessor. The rescaling solves several deep problems. In standard Big Bang theory, we have to ask why the universe started in such a special, low-entropy state. Entropy is a measure of disorder, and our universe began incredibly ordered. Where did that order come from? Penrose's cycles provide an answer. The order comes from the smooth, empty state at the end of the previous cycle. The far future naturally produces the low-entropy conditions needed for a new beginning. There is another advantage. The uniformity of our universe has always puzzled cosmologists. Why does the cosmic microwave background look nearly identical in every direction? Why did regions of space that could never have communicated end up with the same temperature? Standard cosmology invokes inflation, a brief period of faster-than-light expansion, to explain this. But inflation has its own fine-tuning problems. In conformal cyclic cosmology, uniformity emerges naturally from the previous cycle. The long period of expansion in the old universe smooths everything out. When that smooth ending becomes the new beginning, the uniformity carries over. No inflation needed, no special initial conditions required. The universe inherits its properties from cosmic inheritance. Critics point out significant challenges. How exactly does the transition work? What happens to matter that has not decayed? Can information really survive such a dramatic transformation? Penrose admits some details remain unclear, particularly the physics at the crossover surface where one cycle ends and the next begins. He argues this is precisely where quantum gravity must take over, filling in the gaps that classical relativity cannot address. Whether conformal cyclic cosmology is correct remains unknown. What cannot be denied is its elegance. The idea that endings and beginnings are connected, that the universe is eternal and self-renewing, carries a certain beauty. But beauty alone does not make a theory true. The cosmic microwave background is the oldest light in the universe. When astronomers point their instruments at empty space between galaxies, they detect this faint glow. It comes from every direction uniformly, with a temperature of about 2.7 degrees above absolute zero. This radiation was released 380,000 years after the Big Bang, when the universe cooled enough for atoms to form and light to travel freely. Scientists have mapped this glow in extraordinary detail. Satellites like WMAP and Planck measured tiny temperature variations across the entire sky. Some regions are slightly warmer, about 1 part in 100,000 hotter than average. Others are slightly cooler. These variations represent the seeds that eventually grew into galaxies and clusters of galaxies. But Penrose was not looking for these well-known fluctuations. He was hunting for something entirely different: circular patterns indicating Hawking points. According to his theory, supermassive black holes from the previous universe would have gradually evaporated through Hawking radiation. This is a quantum effect where black holes slowly lose mass by emitting particles. For a black hole with billions of solar masses, this process takes an incomprehensible amount of time. We are talking about 10 to the power of 100 years, a duration with 100 zeros after it. Eventually, though, each black hole would completely evaporate in a final burst of energy. These bursts would be the last energetic events in the dying universe. When the conformal rescaling happened, turning the far future into a new Big Bang, these bursts would leave imprints. They would appear as specific types of anomalies in the cosmic microwave background of the new universe. Our universe. Penrose predicted these imprints would look like circular regions where the temperature falls off in a characteristic way from a central hotspot. The circles would have diameters about 5 times the width of the full moon in our sky. They would not be obvious to casual inspection, but statistical analysis should reveal them. In 2010, Penrose and physicist Vahe Gudasadian claimed they found exactly these patterns. They scanned the WMAP satellite data and identified numerous concentric circles where the variance in temperature was significantly lower than expected. They calculated that the probability of seeing so many such circles by random chance was extremely small, less than 1 in a billion. The announcement created immediate controversy. If confirmed, it would revolutionize our understanding of cosmic history. Multiple research teams rushed to check the findings. Within months, 3 independent groups published rebuttals. They analyzed the same data and found no unusual excess of circles. When they created simulated universes using standard cosmology with no previous cycles, those simulations produced just as many circular patterns as the real data. The disagreement came down to methodology. How do you decide what counts as a significant circle? How do you properly generate random simulations to compare against? These technical questions became battlegrounds. Each side accused the other of flawed statistics. Undeterred, Penrose refined his approach. In 2018, he published new analysis with Daniel An and Christoph Meissner. This time, instead of looking for circles with low variance, they searched for concentrated hotspots. They found patches in the cosmic microwave background that were significantly hotter than surrounding regions. Around these hotspots, the temperature gradient was much steeper than in any of their simulated universes. Not a single simulation out of 1,000 matched the real data. They argued these hotspots were exactly what you would expect from Hawking points. The final evaporation of a black hole would inject enormous energy into a small region. That energy would stretch during the early expansion of the new universe, creating a hot patch with a characteristic size and temperature profile. Again, the broader community remained skeptical. Many physicists felt the analysis was comparing apples and oranges. The simulations might not be capturing all the complexity of the real universe. Other groups noted that if you search for enough different patterns in noisy data, you will eventually find something that looks special by chance alone. As of now, the existence of Hawking points remains unproven. The cosmic microwave background is one of the most precisely measured things in science. Yet interpreting its fine details is surprisingly subjective. But one thing is certain: if those hotspots really are echoes from a previous universe, we are not just looking at old light, we are looking at ghosts. The universe today is messy. Galaxies cluster in filaments and sheets. Stars burn and explode. Black holes devour matter. Disorder is everywhere. This messiness is entropy, the measure of how spread out and disorganized energy becomes over time. The second law of thermodynamics states that entropy always increases. Everything tends toward disorder. Your room gets messy unless you actively clean it. Stars eventually burn out. Even atoms decay, given enough time. Yet the Big Bang apparently started in an incredibly ordered state. This is one of cosmology's deepest puzzles. When we look at the cosmic microwave background, we see an almost perfectly smooth universe. Temperature variations of only 1 part in 100,000. No significant clumps, no major irregularities, just gentle ripples in an otherwise uniform sea. This extraordinary smoothness represents extremely low entropy. Where did that order come from? In statistical mechanics, the branch of physics that studies entropy, low entropy states are spectacularly improbable. Imagine throwing a deck of cards into the air. The probability that they land in perfect numerical order is essentially 0. Now imagine that the deck contains not 52 cards, but 10 to the power of 90 particles. That is roughly how many particles exist in the observable universe. The odds of them starting in such an organized configuration are incomprehensibly small. Standard Big Bang cosmology does not explain this initial order. It simply assumes the universe started that way. Physicists call this assumption the past hypothesis. We hypothesize that entropy was very low at the beginning because, well, observations show it was very low. This is not an explanation. This is just restating the puzzle with fancier words. Roger Penrose calculated just how special the initial state actually was. He estimated that the gravitational degrees of freedom at the Big Bang were tuned to a precision of 1 part in 10 to the power of 10 to the power of 123. Let that number sink in. It is 10 with 123 zeros after it, and then you take 10 to that power. Writing it out would require more digits than there are atoms in the universe. This is what Penrose calls the Weyl curvature hypothesis. Weyl curvature measures the type of gravitational field associated with tidal forces and gravitational waves. In an irregular, lumpy universe with black holes and collapsed structures, Weyl curvature is enormous. But at the Big Bang, it was essentially zero. Gravity at the beginning was incredibly smooth and uniform. This smoothness is the source of the universe's low initial entropy. Why would the universe start in such an absurdly improbable state? Cosmic inflation provides one answer. If the universe underwent a brief period of exponential expansion right after the Big Bang, that expansion would have smoothed out any initial irregularities. It is like stretching a wrinkled bedsheet. Pull the edges fast enough at the initial conditions. The far future of the old universe naturally becomes smooth as space expands and matter spreads out. When that smooth ending transitions into a new beginning, the low entropy carries over. The past hypothesis is not an assumption. It is a consequence of cosmic recycling. But this creates another question. What about the entropy from the old universe? If entropy always increases and the new universe inherits conditions from the old, should not each cycle become more disordered than the last? This is called the entropy problem in cyclic cosmology. Some models propose that the universe grows slightly larger with each cycle, providing more room for entropy. Others suggest black holes serve as entropy sinks that somehow reset during the transition. These solutions remain controversial and incomplete. The mathematics of what happens during the bounce or transition is still not fully understood. We are asking questions about physics at energy scales we cannot test in laboratories. At the moment, we only have theories and guesses. What we do know for certain is that the universe's remarkable initial smoothness demands an explanation. Either something extraordinary happened before the Big Bang to set up those conditions, or the Big Bang itself was far more special than our theories suggest. Neither option is easy to accept. Deep beneath the smooth appearance of space lies something profound. Most people think of space as just emptiness, a stage where matter and energy perform their cosmic dance. But quantum physics suggests reality is more complex. Even the vacuum of space has structure, and that structure might save the universe from the singularity problem. Loop quantum gravity is one of the leading approaches to merging quantum mechanics with Einstein's general relativity. It starts with a radical idea: space itself is not infinitely divisible. You cannot keep zooming into smaller and smaller distances forever. Eventually, you hit a fundamental limit called the Planck length, about 10 to the power of minus 35 meters. This is 20 orders of magnitude smaller than a proton. At this scale, space is not continuous. It is granular, made of discrete quantum units. Think of it like pixels on a screen. From far away, an image looks smooth. Up close, you see it is composed of individual colored dots. Space, according to loop quantum gravity, is similarly pixelated at the Planck scale. These pixels are not static. They are dynamic loops of gravitational field, quantum fluctuations that weave together to form the fabric of space-time. The theory gets its name from these loops. Instead of describing gravity as the curvature of smooth space, loop quantum gravity describes it as networks of interconnected loops. These networks are called spin networks, and they represent the quantum state of geometry itself. This picture changes everything about singularities. In classical general relativity, when matter collapses under gravity, it can compress to infinite density at a single point. Infinite density means infinite curvature of space. The equations blow up, physics stops working, but in loop quantum gravity, infinite compression is impossible. You cannot squeeze below the Planck scale because there is no space smaller than a Planck length. As matter collapses and density grows, quantum effects become stronger. When the density reaches the Planck density, about 10 to the power of 93 grams per cubic centimeter, something dramatic happens. Gravity itself becomes repulsive. The collapsing matter bounces back outward. Instead of a singularity, you get a bounce. This prediction led to loop quantum cosmology, a simplified version of the full theory applied to the entire universe. In the early 2000s, physicist Martin Bogerwald showed that when you use loop quantum cosmology to model the Big Bang, the singularity disappears. The universe does not begin from an infinitely compressed point. It rebounds from a previous contracting phase. Imagine running cosmic history backwards. Galaxies get closer together. The universe gets smaller and denser. In standard cosmology, you eventually hit the singularity and your equations break. In loop quantum cosmology, as you approach the Planck density, quantum repulsion takes over. The contraction reverses into expansion. There is no moment of infinite density. The Big Bang becomes a big bounce. Detailed simulations confirm this behavior. Researchers evolved quantum states of the universe forward and backward through the bounce point. The quantum effects smoothly connected contracting and expanding phases. Crucially, some information from the contracting phase survived the bounce. The volume of the universe at its minimum point and the rate of expansion after the bounce depended on conditions before the bounce. This means we could potentially learn about the pre-bounce universe by studying our current universe. Observations of the cosmic microwave background or the distribution of galaxies might contain signatures of quantum gravity effects during the bounce. These would be extraordinarily subtle signals, but they would be real. Loop quantum cosmology also solves another puzzle, the horizon problem. In standard cosmology, distant regions of the universe that have never communicated with each other somehow have nearly identical properties. How did they coordinate their temperatures? Inflation provides one answer by making the observable universe originate from a tiny, causally connected region that then expanded rapidly. Loop quantum cosmology offers an alternative. During the contracting phase, before the bounce, regions that are now far apart were once in contact. They came to equilibrium back then. When the universe bounced and expanded, that equilibrium was preserved. No inflation needed. The theory is not without challenges. Loop quantum gravity itself is incomplete. We do not yet have a full mathematical formulation that works in all situations. The cosmological models are simplified, assuming perfect symmetry that the real universe does not have. Extending the theory to less symmetric situations is incredibly difficult. Moreover, some physicists question whether loop quantum gravity is the right approach at all. Competing theories, like string theory, take completely different paths to quantum gravity. Each approach makes different predictions about what happens at the Planck scale. What is clear is that quantum effects at the smallest scales can have cosmological consequences at the largest scales. Space itself might be the key to understanding where we came from. For decades, the Big Bang was cosmology's founding myth. Everything started from a singular point 13.8 billion years ago. Before that moment, nothing existed. Not space, not time, not even the laws of physics. The Bang was the absolute beginning, and asking what came before was considered meaningless or even unscientific. That certainty is crumbling. Multiple independent lines of research now point toward a bounce rather than a bang. Not a creation from nothing, but a transition from something prior. The universe did not begin, it changed form. This shift in perspective is as profound as the Copernican revolution that displaced Earth from the center of the cosmos. The Big Bounce hypothesis comes in several versions, but they share core elements. Our universe was preceded by a contracting phase. As that previous universe collapsed, instead of forming a singularity, quantum gravity effects intervened. Repulsive quantum forces halted the collapse and reversed it into expansion. This reversal is the bounce. Loop quantum cosmology provides the most developed framework for understanding the bounce. As discussed earlier, the discrete structure of space at the Planck scale prevents infinite compression. When matter density reaches critical values, roughly 10 to the power of 93 grams per cubic centimeter, quantum corrections to Einstein's equations become dominant. These corrections include a repulsive term that grows rapidly at extreme densities. The mathematics shows that the bounce is not instantaneous. There is a brief quantum epoch lasting about 10 to the power of minus 43 seconds, where classical notions of space and time break down. During this period, the universe passes through its minimum volume. Then quantum repulsion takes over completely and drives the expansion we observe. What happened in the contracting universe before the bounce? Here, the evidence becomes speculative. Some models suggest the previous universe was similar to ours, with galaxies and stars just running in reverse time. Others propose the contracting phase had very different properties. The matter content, the spatial geometry, even the effective constants of nature might have differed. One intriguing possibility is that information could survive the bounce. Unlike black hole singularities, where information appears to be destroyed, the bounce is smooth enough that quantum states might pass through. The scalar fields representing matter and energy evolve continuously. Their values after the bounce depend on their values before. This creates what physicists call a quantum bridge connecting the two phases. If information survives, then relics from the pre-bounce universe could exist in ours. These would not be physical objects. Atoms and molecules could not survive the extreme conditions near the bounce. But subtle correlations in the quantum fields might persist. These correlations could show up as specific patterns in cosmological observations. Several research groups have calculated what the cosmic microwave background should look like if our universe bounced. The predictions depend sensitively on the details of the bounce dynamics, but some generic features emerge. The spectrum of temperature fluctuations might have slight deviations from the standard predictions. The amount of gravitational waves produced during the bounce could differ from inflation. The distribution of matter on large scales might carry subtle signatures. So far, observations have not definitively detected any bounce signatures. The cosmic microwave background matches standard inflationary predictions remarkably well, but the precision of current measurements is limited. Future experiments with higher sensitivity might reveal small anomalies that point to a bounce. Critics raise several objections to bounce cosmology. The biggest concern is whether the bounce truly avoids a singularity or merely delays it. Some analyses suggest that even with quantum corrections, certain types of anisotropic collapses still lead to singularities. If the universe was not perfectly symmetric before the bounce, would it still bounce cleanly? Another worry is fine-tuning. For a bounce to produce a universe like ours, conditions at the bounce point must be carefully arranged. The quantum state needs specific properties. The amount of matter and its distribution must fall within narrow ranges. If the pre-bounce universe was chaotic and irregular, could the bounce really smooth everything out? These technical debates continue in academic journals. What is remarkable is that mainstream physics now seriously considers the possibility of a pre-existing universe. The Big Bounce is no longer fringe speculation. It is a legitimate scientific hypothesis with mathematical rigor and potential observational tests. The implications are staggering. If the bounce is real, then the universe has a history extending infinitely into the past. Or perhaps there was an earliest bounce, a first transition, and the mystery simply moves back to that moment. Either way, the Big Bang loses its status as the ultimate origin. We are not witnessing the beginning of existence. We are watching one phase in an ongoing process. The idea of universes connected by a quantum bridge sounds like science fiction, but in loop quantum cosmology, it emerges naturally from the mathematics. This bridge is not a physical structure you could see or touch. It is a continuous mathematical evolution that links the contracting phase to the expanding phase without ever reaching zero volume. To understand the quantum bridge, you need to grasp how quantum mechanics treats evolution. In classical physics, objects have definite positions and velocities at each moment. You can predict precisely where a ball will be if you know where it started and how fast it was moving. In quantum mechanics, particles do not have definite positions until measured. They exist in superpositions, spread across multiple possible locations simultaneously. The universe in loop quantum cosmology is described by a quantum state, a mathematical object called a wave function. This wave function encodes the probabilities of finding the universe with different volumes and matter contents. As time progresses, the wave function evolves according to quantum equations. This evolution is unitary, meaning information is preserved and nothing is truly lost. When the universe contracts, its wave function evolves towards smaller and smaller volumes. In classical general relativity, this evolution would hit a singularity at zero volume and stop. The equations would produce infinities and meaningless results. But in loop quantum cosmology, the evolution does not stop. The wave function smoothly passes through the region of minimum volume and emerges on the other side, corresponding to an expanding universe. This passage through the minimum is the quantum bridge. It is called a bridge because it connects two distinct cosmological phases. Before the bridge, the universe was contracting. After the bridge, the universe expands. The bridge itself lasts for the briefest instant, roughly 1 Planck time, about 10 to the power of minus 43 seconds. During this instant, classical concepts like volume and time become fuzzy. You cannot ask, what was the exact volume at this precise moment? The question assumes a level of definiteness that quantum mechanics does not allow at such extreme scales. What you can ask is, what is the probability distribution for volumes, and how does that distribution evolve? Calculations show the distribution remains well behaved throughout the bounce. It does not spike to infinity. It does not develop discontinuities. The universe does not blink out of existence and reappear. It continuously exists as a quantum system, even if our classical intuitions about space and time fail. One key feature of the quantum bridge is that it preserves certain quantities called observables. In quantum mechanics, observables are properties you can, in principle, measure. For cosmology, important observables include the total energy content, the spatial curvature, and the values of various matter fields. The quantum bridge allows these observables to pass through the bounce point with specific relationships maintained. For example, consider a scalar field representing a type of matter. This field has a value at each point in space and evolves over time. If you know the field's behavior during contraction, you can calculate its behavior after the bounce using loop quantum cosmology. The two are linked. The scalar field after does not start with random values. It inherits structure from the scalar field before. This inheritance is crucial for making predictions. If we can measure the properties of our universe precisely enough, we might be able to reconstruct properties of the pre-bounce universe. This would be indirect detection, like inferring the shape of an object from its shadow. The measurements would be extraordinarily difficult, requiring precision beyond current technology, but they are possible in principle. Different scalar fields might carry different types of information. Inflaton fields, if they exist, could encode data about pre-bounce energy densities. Curvaton fields might preserve information about spatial geometry. Even the pattern of quantum fluctuations seeded during the bounce could reflect pre-bounce conditions. However, not all information survives. There is an effective uncertainty principle operating at the bounce. Just as you cannot simultaneously know a particle's position and momentum with perfect precision, you cannot simultaneously know all properties of the pre-bounce and post-bounce universes with perfect precision. some details are inevitably lost or scrambled by the quantum nature of the bounce. Physicists describe this using a transfer function, a mathematical rule that maps pre-bounce states to post-bounce states. The transfer function is not one-to-one. Multiple different pre-bounce states could lead to the same post-bounce state. This means we cannot uniquely determine the entire history of the contracting universe just by studying the expanding one. Some ambiguity is fundamental. Despite this limitation, the quantum bridge represents a profound shift in cosmological thinking. It suggests the universe is not fragmented into disconnected epochs. Past, present, and future are linked by continuous quantum evolution. The bounce is not a wall blocking our knowledge. It is a gateway, admittedly narrow and obscure, but a gateway nonetheless. What lies on the other side of the quantum bridge remains largely mysterious, but we now have theoretical of a trillionth of a second. The universe doubled in size, at least 90 times. Space expanded faster than light. This rapid growth smoothed out irregularities and flattened the geometry, solving several major cosmological puzzles. Inflation quickly became the leading theory of the early universe. But as physicists explored the mathematics more deeply, they discovered something unexpected. Inflation does not just happen once and stop everywhere at the same time. In most versions of the theory, inflation is eternal. Once it starts, it never completely ends. Here is how eternal inflation works. Imagine the universe filled with an energy field called the inflaton. This field drives inflation when its energy density is high. As inflation proceeds, the field gradually decays into lower energy states. In regions where it decays, inflation stops and a hot Big Bang begins. That region becomes a pocket universe, like ours. But here is the catch. Space is expanding exponentially. Even though inflation ends in some places, the expanding regions between those places grow faster than the non-inflating regions can fill them. New volume is created faster than old volume can convert. The total amount of inflating space increases without limit. More and more pocket universes form forever. Think of it like foam on the ocean. Each bubble represents a pocket universe where inflation ended. The foam between bubbles is still inflating, creating new bubbles endlessly. You can pop individual bubbles, but the foam itself never stops growing. The process is self-sustaining and eternal into the future. Quantum fluctuations make this inevitable. The inflaton field is subject to quantum jitter. In some tiny patches, random fluctuations push the field up the energy hill instead of down. Those patches inflate longer and produce more volume. Even if inflation is unlikely to start, once it starts anywhere, it runs away exponentially. The inflating regions dominate the universe's total volume. André Linde, one of the pioneers of inflation theory, proved in 1986 that eternal inflation is generic. You do not need special conditions. Almost any inflation model leads to eternal inflation unless you carefully design the theory to avoid it. Guth confirmed this in later work. He famously said, "It is hard to build models of inflation that do not lead to a multiverse." The multiverse, arising from eternal inflation, is vast beyond comprehension. It is not just billions of pocket universes. It is infinite. Every possible way that inflation could end happens infinitely many times in different places. Every possible set of physical constants that could emerge from the inflaton's decay appears somewhere. This leads to extraordinary conclusions. In an infinite multiverse, everything that can happen does happen. Not just once, but infinitely many times. There are infinite copies of Earth, infinite copies of you, infinite versions where you made different choices, infinite universes with different physics entirely. Most physicists find this deeply unsettling. Science is supposed to make predictions, but if anything possible occurs somewhere in the multiverse, how do you predict what we should observe in our universe? This is called the measure problem. You cannot calculate probabilities in the usual way when dealing with infinity. Some physicists embrace the multiverse as a feature, not a bug. It explains the cosmological constant problem. In our universe, the vacuum energy density is incredibly small, about 10 to the power of minus 120 in natural units. Theory suggests it should be 10 to the power of 120 times larger. Such a massive discrepancy seems impossible to explain. But in a multiverse with infinite variety, some universes will randomly have small vacuum energy. We live in one of those because universes with large vacuum energy do not form stable galaxies and stars. Observer selection does the rest. Other physicists hate this reasoning. They argue it is giving up on fundamental physics. Instead of deriving the cosmological constant from first principles, the multiverse says it is just environmental, like asking why Earth's distance from its star is 93 million miles. The answer is not deep physics. It is just that we need the right distance to support life. The debate over eternal inflation and the multiverse it implies remains unresolved. Some researchers are looking for ways to test multiverse predictions. If other pocket universes collided with ours during inflation, they might have left imprints in the cosmic microwave background. These collision signatures would appear as specific patterns of temperature variation. So far, no such collisions have been detected, but the search continues. Advanced telescopes and detectors coming online in the next decade might find subtle anomalies that standard single-universe theories cannot explain. What is clear is that inflation, originally designed to solve simple problems, opened Pandora's box. It transformed cosmology from studying the universe into contemplating a multiverse. The Big Bang is no longer unique. It is one event among infinite others, occurring eternally in an ever-expanding sea of space. We thought discovering the universe was enough. Instead, we learned the universe is just the beginning. Alan Guth did not set out to destroy the uniqueness of our universe. He was a theoretical physicist struggling with a specific technical problem in particle physics. The solution he found in December 1979 solved that problem beautifully. It also inadvertently implied our universe is just one bubble in an infinite foam. Guth was thinking about magnetic monopoles. These are hypothetical particles predicted by grand unified theories that attempt to merge three of the four fundamental forces. The problem was that these theories predicted monopoles should be everywhere. Every cubic meter of space should contain billions of them. Yet astronomers had never detected a single magnetic monopole. This was called the monopole problem. Guth realized that if the early universe inflated exponentially, it would dilute monopoles to undetectable levels. Inflation would spread the few monopoles created in the Big Bang across such vast distances that we would never encounter one. Problem solved. He wrote spectacular realization in his notebook that night. But he also noted a serious issue that would take years to resolve. The original inflation model assumed the universe started in a state called false vacuum, a temporary high-energy configuration that wanted to decay into a lower-energy true vacuum. As the false vacuum decayed, it released energy that drove inflation. The decay happened through quantum tunneling, where bubbles of true vacuum formed and expanded. The problem was, these bubbles expanded at light speed, but could not catch up to the inflating space around them. The false vacuum between bubbles kept inflating faster than the bubbles grew. The bubbles could never merge to fill all space. The universe would remain forever fragmented, with patches of true vacuum surrounded by false vacuum. This did not match observations. Our universe looks smooth and connected. Andre Linde and Andreas Albrecht, with Paul Steinhardt, independently fixed this problem by modifying how inflation ended. Instead of bubbles tunneling, the inflaton field slowly rolled down an energy hill, causing inflation to end more gracefully. This new inflation solved the fragmentation issue, but it also guaranteed eternal inflation, because quantum fluctuations would always push the field back up the hill in some regions. Guth and Linde both realized what this meant. If inflation was truly eternal, it produced an infinite number of separate pockets. Another attempt to unify physics. also predicted a vast landscape of possible vacuum states, reinforcing the multiverse concept. Guth and Linde became spokesmen for the idea that our observable universe is just one random sample from an infinite ensemble. This created philosophical and scientific challenges. If we live in just one bubble among infinite bubbles, how do we test our theories? Traditional science compares predictions to observations, but multiverse theories often predict that every outcome occurs somewhere. How do you falsify a theory that predicts everything? Some physicists argue we should use anthropic reasoning. We observe what we observe because we exist. Universes with very different properties would not produce observers like us. So even in an infinite multiverse, we should expect to find ourselves in a universe compatible with our existence. This anthropic principle lets us make probabilistic predictions based on which universe properties are most conducive to life. Others find anthropic reasoning unsatisfying. It feels like giving up on deep explanations. Instead of asking why the physical constants have the values they do, anthropic reasoning says those values are environmental accidents. In another bubble, they are different. We happen to be in a life-friendly bubble. End of story. Guth himself is pragmatic about the multiverse. He acknowledges it is a radical conclusion that makes science more difficult. But he also points out that science follows where the evidence leads, even to uncomfortable places. Inflation is strongly supported by observations of the cosmic microwave background. If inflation naturally leads to eternal inflation, and eternal inflation naturally leads to a multiverse, then we must take the multiverse seriously. The multiverse implies our cosmic history is bizarre. The Big Bang was not the beginning of reality. It was the beginning of our local pocket. Before our bang, the larger, inflating space already existed, continuously producing new pockets. Some of those pockets formed earlier than ours. Some will form later. Our universe's 13.8 billion year age is just the time since our pocket's inflation ended. There might be no ultimate beginning at all. The inflating space could be eternally old with no first moment, or there could have been some initial event that started inflation, but that event is lost in the infinite past, inaccessible to us by any means. We are trapped in our bubble, unable to see beyond the horizon that light has had time to cross. Guth's spectacular realization was more spectacular than he imagined. He thought he was solving a problem about magnetic monopoles. He accidentally discovered that we live in an infinite cosmos where every possibility is realized. The universe is not a single story. It is an infinite library where every story is written. Empty space is not as empty as it seems. Quantum field theory, the mathematical framework describing particle physics, reveals that what we call a vacuum is teeming with activity. Virtual particles constantly pop in and out of existence. Fields permeate every point. Energy fluctuates wildly at tiny scales. These quantum properties mean vacuum can have different states, like water existing as ice, liquid, or vapor. Each state has a different energy density. The lowest energy state is called the true vacuum. Higher energy states are called false vacuums. If the universe is currently in a false vacuum, it could potentially decay into a lower energy state with dramatic consequences. False vacuum decay was first analyzed in the 1970s by Sidney Coleman and others. They calculated how a region of false vacuum could tunnel quantum mechanically into true vacuum. The process begins with a random quantum fluctuation that creates a tiny bubble of true vacuum. This bubble has lower energy than the surrounding false vacuum. The energy difference creates pressure that causes the bubble to expand. Once formed, the bubble wall moves outward at nearly the speed of light. Inside the bubble, the laws of physics might be completely different from outside. Particles could have different masses. Forces could have different strengths. The cosmological constant could change value. For anyone inside, the passage of the bubble wall would be catastrophic. All complex structures would disintegrate. False vacuum decay provides the mechanism for eternal inflation in many models. Imagine the inflaton field starts in a false vacuum with enormous energy density. This high energy drives exponential inflation. Occasionally, quantum tunneling produces bubbles where the field has decayed to a lower energy state. Inside these bubbles, inflation slows or stops, and a hot Big Bang begins. But here is the twist that makes inflation eternal. The false vacuum is still inflating between the bubbles. Space expands so fast that even though bubbles keep forming, they can never fill all available space. The volume of inflating false vacuum grows faster than the volume converts to true vacuum. Inflation continues forever in most of space, while pocket universes form as islands in an inflating sea. This picture has profound implications. Our universe is such a pocket. Inflation ended here about 13.8 billion years ago, when the local patch of false vacuum decayed. But beyond our cosmic horizon, far beyond what our best telescopes could ever see, inflation continues. New pockets form constantly. Each pocket is causally disconnected from the others. Light from another pocket cannot reach us because the inflating space between us expands too rapidly. The energy released during false vacuum decay becomes the matter and radiation in the new pocket. This is called reheating. The inflaton field's potential energy converts into a hot soup of particles. This is the Big Bang, the moment of maximum temperature and density. From that point, standard Big Bang cosmology takes over. The universe expands and cools. Atoms form, stars ignite, galaxies assemble. Different pockets might have different properties depending on how and where the false vacuum decayed. String theory suggests the inflaton can settle into many possible low-energy configurations, each corresponding to different particle physics. One pocket might have 3 generations of quarks and leptons like ours. Another might have 7. One might have a strong nuclear force, twice as strong as ours. Another might lack electromagnetism entirely. This diversity makes the multiverse a laboratory containing every possible experiment. Somewhere, a pocket exists where electrons are heavier than protons. Somewhere, atoms cannot form. Somewhere, chemistry is unrecognizable. And somewhere, tucked into a corner with just the right properties, observers evolve and wonder why their universe seems so finely tuned for life. But could we still be in a false vacuum? Could our current universe be metastable, capable of decaying to an even lower energy state? Calculations suggest this is possible. The measured mass of the Higgs boson and the top quark place our universe near the boundary between stability and metastability. Small changes in either value would push us definitively into the false vacuum regime. If we are in a false vacuum, decay could happen at any moment. A bubble of true vacuum could nucleate anywhere in space tomorrow. Once formed, it would expand at light speed. We would have no warning. The bubble wall would arrive without announcement, erasing everything we know. The interior might support different physics, but probably not chemistry or life as we understand it. Fortunately, calculations indicate such decay is extraordinarily unlikely on human timescales. The probability per cubic meter per year is absurdly small, many orders of magnitude below anything we could detect. The universe could persist in its current state for durations vastly exceeding its current age. By the time false vacuum decay becomes likely, all stars will have died and all black holes evaporated anyway. Still, the idea that reality itself could collapse at any instant remains disturbing. It also offers a strange kind of immortality to the multiverse. Even if our pocket universe eventually decays, countless others exist unaffected. The multiverse as a whole is eternal. Individual pockets are temporary. The false vacuum is both a trap and a gateway. It traps us in a temporary island of stability, but it also serves as the gateway through which new universes are born. We are living on borrowed energy. Look around you. Space has 3 dimensions. You can move forward, backward, left, right, up, down. Add time as the 4th dimension, and you have the space-time of relativity. 4 dimensions explain everything we observe. Or do they? String theory the leading candidate for unifying quantum mechanics and gravity, requires more dimensions. Not just 1 or 2 extra dimensions, but 6 additional spatial dimensions beyond the 3 we see. That means space has 9 dimensions, plus time makes 10. In some versions of the theory, called M-theory, there are 11 dimensions total. This seems absurd. Where are these extra dimensions hiding? The answer is they are curled up so small we cannot detect them. Imagine a garden hose viewed from far away. It looks like a one-dimensional line. Only up close do you see it has thickness, with a circular dimension wrapped around the length. The extra dimensions of string theory are similar, rolled into microscopic shapes smaller than subatomic particles. These hidden dimensions are not just mathematical artifacts. They profoundly affect physics. The size and shape of the extra dimensions determine properties of particles and forces in the visible dimensions. A string vibrating in 10 dimensions can produce different patterns depending on how those extra dimensions are configured. Each pattern corresponds to a different particle. This gives string theory tremendous flexibility. By choosing different geometries for the extra dimensions, you can reproduce the particles and forces of the standard model. You can also produce entirely different physics. String theorists estimate there are roughly 10 to the power of 500 possible configurations of the extra dimensions. Each configuration gives a different low-energy physics. This vast landscape of possibilities is both a blessing and a curse. It explains why string theory can accommodate so many features of nature, but it also means the theory does not uniquely predict our universe's properties. Many different compactifications could produce physics similar to what we observe. Without a principle for selecting the right compactification, string theory loses predictive power. The extra dimensions have another remarkable property. They allow for extended objects larger than one-dimensional strings. A two-dimensional surface extending through space is called a membrane or brane. Higher dimensional objects are possible too. Our familiar three-dimensional space might actually be a three-brane, a sheet embedded in the higher dimensional space. This brane world picture revolutionized cosmology in the late 1990s. Physicists realized that if we live on a brane, the particles and forces we know about might be confined to that brane. Only gravity could propagate through the full higher dimensional space called the bulk. This explained why gravity is so much weaker than other forces. Gravity dilutes across extra dimensions, while electromagnetic and nuclear forces stay concentrated on our brane. The brane world concept led to the ekpyrotic scenario, proposed by Paul Steinhardt, Neil Turok, and collaborators in 2001. This model suggests our universe is a three-brane floating in a higher dimensional bulk. Nearby, separated by a gap across an extra dimension, floats another parallel brane. These two branes are attracted to each other by gravitational forces acting through the bulk. Occasionally, the branes collide. When they crash together, the collision releases enormous energy. This energy appears as hot matter and radiation on the branes. From the perspective of anyone on the brane, this looks like a big bang, but it is not the beginning of space or time. It is just a collision event in an ongoing history. After the collision, the branes bounce apart, move back through the bulk, slow down, and eventually start approaching again. The cycle repeats. Each collision is a new Big Bang. Each separation creates time for a universe to evolve before the next collision. This is the cyclic ekpyrotic model. The extra dimension plays a crucial role. The distance between branes changes as they move through this dimension. When they are far apart, the distance grows as the universe expands. When they collide, the extra dimension momentarily shrinks to zero before growing again. This provides a natural mechanism for generating cycles without ever having a singularity where all dimensions collapse. The ekpyrotic scenario makes specific predictions about the cosmic microwave background that differ slightly from standard inflation. It predicts less gravitational wave production and different patterns in the temperature fluctuations. Observations so far favor inflation, but the differences are subtle. More precise measurements might distinguish between the models. String theory's extra dimensions also affect black holes. A black hole in 4-dimensional spacetime has a simple geometry, but a black hole in 10 dimensions can have complex topologies involving the extra dimensions. These higher dimensional black holes might behave differently, affecting how they form, merge, and evaporate. Some string theorists speculate that the Big Bang itself was a higher dimensional black hole. From outside, it would look like a collapsing object. From inside, it would appear as an expanding universe. This black hole cosmology remains highly speculative, but it shows how extra dimensions provide new ways to think about cosmic origins. Critics point out that string theory's extra dimensions have never been observed. No experiment has detected even the slightest hint of dimensions beyond the familiar 3. The theory's mathematical elegance does not guarantee physical reality. Many physicists suspect the true quantum theory of gravity might not require extra dimensions at all. Nonetheless, the idea that space has hidden structure profoundly influenced modern cosmology. It opened conceptual possibilities that researchers continue to explore. The ekpyrotic model, brane collisions, and cyclic universes all flow from taking extra dimensions seriously. Reality might have more directions than we can imagine, and what we call the universe might be just a surface in a deeper space. Picture 2 enormous sheets of reality floating through a higher dimensional void. Each sheet is a 3-brane, a 3-dimensional surface extending infinitely in the directions we experience as space. These branes are separated by a small gap in an extra dimension we cannot see. They are being pulled together by gravitational attraction, acting through the bulk. As the branes approach, they accelerate. The gap narrows. At some point, they collide with tremendous energy. The collision heats both branes to extraordinary temperatures. Matter and radiation flood across their surfaces. From the perspective of any observer on a brane, this appears as a Big Bang, a sudden transition from cold emptiness to a hot, dense state. This is the ekpyrotic scenario's central mechanism. The word ekpyrotic comes from ancient Greek philosophy, referring to a cosmology where the universe is born from fire and returns to fire in an eternal cycle. Modern ekpyrotic theory translates this into string theory mathematics. The Big Bang is not a beginning from nothing. It is a collision of branes. Paul Steinhardt and Neil Turok developed this picture in 2001 while working on problems in string theory and cosmology. They were motivated by issues with both standard Big Bang theory and cosmic inflation. Inflation requires very special initial conditions and introduces a multiverse that bothered them. They wanted a model that was simpler and more predictive. The ekpyrotic scenario starts with 2 parallel branes separated by a distance in an extra dimension. Initially, both branes are cold, flat, and nearly empty. Quantum fluctuations create small ripples on their surfaces, but overall, they are smooth. An attractive force between the branes, interpreted as a type of potential energy, causes them to slowly drift toward each other. As they approach, the potential energy converts to kinetic energy. The branes pick up speed. When they finally collide, the kinetic energy converts into heat and matter on the branes. This heating is the Big Bang. The temperature spikes to levels similar to what standard cosmology predicts for the early universe. Particles are created in vast numbers. The universe becomes a hot soup of fundamental constituents. After the collision, the branes bounce apart. The repulsive force generated during the collision pushes them back into the bulk. They separate, and the universe on each brane expands and cools. Galaxies form, stars ignite, life might emerge. Meanwhile, the branes continue moving apart until the attractive force halts them and starts pulling them together again. The cycle repeats endlessly. Collision, bounce, separation, return, collision. Each cycle lasts trillions of years. Our current universe, 13.8 billion years old, is just the early part of one cycle. Eventually, in the distant future, dark energy will cause our brain to accelerate away from its partner. But ultimately, the attraction will bring them back together for the next collision. This cyclic model has several advantages over standard Big Bang cosmology. It naturally explains why the universe started in a smooth, flat state. The slow approach of the brains before collision allows quantum fluctuations to create uniform patterns. No inflation needed to smooth out irregularities. The smoothness comes from the pre-collision dynamics. It also addresses the entropy problem. In standard cosmology, the universe begins in an extraordinarily low entropy state for no apparent reason. In the ekpyrotic model, each cycle adds entropy. But the expansion between collisions provides more phase space, allowing entropy to increase without causing problems. The universe can be both cyclic and obey the second law of thermodynamics. The model makes testable predictions. During the collision, the brains generate density perturbations, but very few gravitational waves. This is opposite to inflation, which produces substantial gravitational waves. Future detectors, measuring primordial gravitational waves, could distinguish between the scenarios. If the signal is much weaker than inflation predicts, ekpyrotic cosmology gains support. However, the ekpyrotic model faces significant challenges. The biggest is the singularity problem. Just because you describe the Big Bang as a brain collision does not mean you have avoided singularities. At the moment of collision, energy densities and temperatures become infinite within the standard mathematical framework. The brain collision is still a singularity, where general relativity breaks down. Proponents argue that string theory, when fully understood, will resolve this singularity. String theory replaces point particles with extended strings, naturally smoothing out extreme concentrations of energy. But string theory is not yet complete enough to rigorously calculate what happens during a brain collision. The singularity remains a problematic gap in the model. Another issue is fine-tuning. For the brains to collide in a way that produces our observed universe, many parameters must be set carefully. The attractive force needs just the right strength. The initial separation must fall within a narrow range. The quantum fluctuations must have specific properties. Critics argue ekpyrotic cosmology trades one set of fine-tuning problems for another. Despite these challenges, the ekpyrotic scenario profoundly influenced cosmological thinking. It demonstrated that the Big Bang does not necessarily represent the beginning of time. Alternatives exist, where our cosmic history extends far into the past. Whether brains literally exist or not, the conceptual possibility they illustrate is important. The collision of vast structures in higher dimensions, producing our reality as a side effect, is a humbling idea. It suggests our universe is less special than we imagined, just an impact in an ongoing story. One moment when two surfaces briefly touched, igniting existence. The ancient Stoic philosophers imagined a universe born from fire, destroyed by fire, and reborn from fire again in an endless cycle. They called this ekpyrosis, the cosmic conflagration. Every few thousand years, the world would end in flames and begin anew. The cycle had no ultimate start or finish. It simply was, eternally repeating. Modern physics has revived this concept with mathematical precision. The ekpyrotic scenario is not mysticism. It is a rigorous model based on string theory that happens to echo ancient intuition. The fire is now understood as the enormous energy released when two brains collide. The rebirth is the new universe that forms on those brains after collision. The cycle continues indefinitely. The ekpyrotic model addresses several deep cosmological puzzles simultaneously. Start with the flatness problem. Our universe has very nearly flat spatial geometry, but in standard Big Bang theory, flatness is unstable. Any slight deviation from perfect flatness gets amplified over time. For the universe to be as of the cosmic microwave background, have nearly identical temperatures, despite being too far apart to have ever communicated at light speed. How did they coordinate? Standard cosmology invokes inflation to make distant regions start close together. Ekpyrotic cosmology uses the contracting phase. During contraction, regions that are now separated were once in causal contact. They equilibrated back then. The scenario makes specific predictions about primordial density perturbations. These are the tiny variations in matter density that eventually grew into galaxies. In inflation, quantum fluctuations during the exponential expansion produce these perturbations with a nearly scale-invariant spectrum. Different-sized regions have similar amplitude fluctuations. Ekpyrotic cosmology produces a similar spectrum, but through a different mechanism. Quantum fluctuations during the contracting phase get amplified as the branes approach collision. The amplification is scale-dependent in just the right way to match observations. Crucially, ekpyrotic models predict almost no gravitational waves, unlike inflation, which produces a significant gravitational wave background. This difference provides a clear observational test. Experiments like LIGO and future space-based detectors aim to measure primordial gravitational waves. If they find waves at the level inflation predicts, ekpyrotic cosmology is ruled out. If they find much weaker signals or none at all, ekpyrotic models gain credibility. Current observations slightly favor inflation, but sensitivity is not yet high enough for a definitive verdict. The cyclic version of ekpyrotic cosmology extends the single collision into an infinite series. After each collision and expansion, the branes eventually fall back together for another collision. Dark energy plays a crucial role. The accelerated expansion we observe today, driven by dark energy, is interpreted as a force pushing the branes apart, but this force is not repulsive forever. At large separations, the attractive force dominates and pulls the branes back. This sets up a rhythm: collision, expansion, turnaround, contraction, collision. Each complete cycle might last several trillion years. Our universe is currently in the expansion phase of one cycle. Eventually, in the unimaginably distant future, expansion will halt and contraction will begin. The universe will shrink slowly over trillions of years until the next collision ignites a new Big Bang. One fascinating implication is that the future and past are connected. The far future of our universe becomes the pre-collision state for the next cycle. This means studying the eventual fate of our cosmos might reveal clues about what came before our Big Bang. The physics of dying universes and newborn universes are linked. Some physicists find the cyclic ekpyrotic model more satisfying than eternal inflation because it avoids the multiverse. There is only one universe going through cycles, not infinite bubble universes with different physics. This makes the theory more predictive. We are not asking why our universe has certain properties out of infinite possibilities. We are asking how the cyclic dynamics select those properties. Critics point to several unresolved issues. The singularity at the collision remains problematic. String theory should resolve it, but the calculations are beyond current techniques. There are also questions about entropy. Does entropy reset at each collision, or does it accumulate? If it accumulates, each cycle should become longer and more chaotic. Observations do not show signs of such progression. Despite these challenges, the ekpyrotic scenario represents bold thinking. It takes seriously the possibility that time is truly infinite in both directions. The universe has no beginning and no end. It cycles through phases like seasons, each one setting up the next. We live in the spring of one cosmic year, with autumn and winter eventually ahead, followed by another spring. Ancient Stoics had no mathematics, no telescopes, no quantum mechanics. Yet their intuition about eternal cycles captures something that modern physics increasingly considers plausible. Perhaps humans have always sensed that reality is older and stranger than any beginning can explain. There is a number in physics so puzzling that Steven Weinberg called it the bone in our throat. This number describes the energy of empty space itself. Quantum field theory predicts its value should be enormous, about 120 orders of magnitude larger than observed. This discrepancy is so vast, it defies comprehension. It is the worst theoretical prediction in the history of science. The number is called the cosmological constant, denoted by the Greek letter lambda. Einstein introduced it in 1917 as a modification to general relativity, then later abandoned it, calling it his biggest blunder. But astronomical observations in 1998 revealed that lambda is not zero. Empty space does have energy. It causes the universe's expansion to accelerate. We see this acceleration when we measure distant supernovae. They appear dimmer than expected, indicating greater distances than standard expansion would produce. The problem is quantum mechanics predicts vacuum should be seething with energy. Virtual particles pop in and out of existence constantly. Each type of particle contributes to the vacuum energy. Add up all contributions from all particle types up to the Planck energy scale, and you get a vacuum energy density of about 10 to the power of 93 grams per cubic centimeter. This is fantastically large. Actual measurements show the vacuum energy density is about 10 to the power of minus 27 grams per cubic centimeter. The ratio between theory and observation is about 10 to the power of 120. To visualize this, structures like galaxies, stars, planets, and us to exist. Some physicists hoped lambda was exactly zero due to some unknown symmetry. That would at least be elegant. But the observations showing lambda is small but positive rule out this explanation. The universe has vacuum energy. It is just incredibly less than theory predicts. Why? Cyclic cosmology offers a potential answer. If the universe goes through infinite cycles, the cosmological constant could be decreasing over time. Each cycle bleeds off some vacuum energy. After countless cycles stretching into the infinite past, lambda has relaxed to a tiny value. We observe this small constant not because our universe is special, but because it has aged through many cycles. This explanation appeals to physicists who dislike anthropic reasoning. The alternative explanation, favored by multiverse advocates, is environmental. In eternal inflation, different pocket universes have different values of lambda, selected randomly from a vast landscape of possibilities. Most pockets have large lambda and remain empty. We live in a rare pocket with small lambda because only such pockets produce observers. We observe what we must observe to exist. Cyclic models avoid this anthropic logic. There is one universe with one value of lambda, and that value results from cosmological evolution through cycles. The theory makes a definite prediction that lambda should be small today and provides a mechanism for why. This is more satisfying to physicists who want fundamental explanations rather than selection effects. However, the cyclic explanation faces challenges. If lambda decreases each cycle, it must have been larger in past cycles. But if it was too large even a few cycles ago, the universe would have accelerated too fast for structures to form. How did the cyclic process get started? There seems to be a fine-tuning problem pushed back to earlier cycles. Another approach uses string theory's landscape of vacuum states. Perhaps there are thousands of competing effects that determine lambda, each pulling it in different directions. The observed tiny value results from delicate cancellations among these effects. But this seems contrived. Why should nature arrange such perfect cancellations? Some physicists argue we simply do not understand quantum field theory well enough. The calculation predicting huge vacuum energy might be wrong. Perhaps there are fundamental principles we have not discovered that naturally make lambda small. Supersymmetry, if it exists, could provide partial cancellations. But even supersymmetry only reduces the discrepancy from 10 to the power of 100, 20 to 10 to the power of 60. Still absurdly large. The cosmological constant problem is deeply connected to quantum gravity. At the Planck scale, where quantum effects and gravitational effects become equally important, space itself becomes quantized. Our current calculations assume space-time is a smooth continuum. Maybe that assumption fails at the Planck scale, and the corrected calculation gives a small lambda. Loop quantum gravity and other approaches to quantum gravity might resolve the problem, but no complete calculation exists yet. We are stuck with the mystery. The vacuum energy is tiny, yet the universe accelerates. This small constant dominates cosmic evolution and will determine the ultimate fate of everything. In the far future, tens of billions of years from now, dark energy will overwhelm gravity everywhere. Galaxies will separate beyond each other's horizons. Eventually, even atoms might be torn apart in a big rip, or the acceleration might continue more gently, leading to a cold, dark, empty cosmos. Either way, lambda shapes destiny. The cosmological constant problem illustrates our ignorance. We do not understand the vacuum. We do not understand how quantum mechanics and gravity merge. We are missing something fundamental about reality. Perhaps the answer lies before the Big Bang. Run the universe backwards in time. Galaxies merge. Space contracts. Matter grows denser. In standard cosmology, you hit the singularity and the story ends. But string theory suggests something radical. Keep running the film in reverse, and the universe does not collapse into nothing. It transforms into something else entirely. Pre-Big Bang cosmology was developed by Gabriele Veneziano and Maurizio Gasparini in the early 1990s. They noticed that string theory equations have a special symmetry. If you take a solution describing an expanding universe and flip certain variables, you get another valid solution describing a contracting universe. These two solutions can be connected through what looks like a Big Bang in between. The key player is a field called the dilaton. This field determines the strength of all forces in string theory. When the dilaton has a low value, forces are weak. When it has a high value, forces are strong. In pre-Big Bang cosmology, the dilaton starts at low values in the distant past. Forces are incredibly weak. The universe is cold, large, and nearly empty. Quantum fluctuations in this cold universe slowly cause the dilaton to increase. As the dilaton grows, gravity becomes stronger. The universe begins to contract. But this is not ordinary gravitational collapse. The dilaton field drives the contraction in a controlled way. The process accelerates gradually over enormous timescales. As contraction continues, the universe shrinks and heats up. Density increases. Curvature grows. The dilaton keeps rising. Eventually, the universe reaches a critical density where stringy effects become important. Strings are not point particles. They have size, about the Planck length. When the universe compresses to this scale, string physics takes over. At maximum compression, something remarkable happens. The string equations show that contraction can transition to expansion. The universe bounces. This bounce is not caused by quantum gravity repulsion, like in loop quantum cosmology. It is caused by fundamental string symmetries. The dilaton reaches a maximum value and starts decreasing. Gravity weakens. Contraction reverses into expansion. After the bounce, we have the universe we observe. Hot, dense, expanding. The dilaton slowly decreases as the universe grows. Forces weaken over time. This is our post-Big Bang phase. But crucially, there was a pre-Big Bang phase before it. The Big Bang was not the beginning. It was a transition from contraction to expansion, mediated by string theory. Pre-Big Bang cosmology makes several predictions. One involves gravitational waves. During the contracting phase, the dilaton amplifies gravitational wave fluctuations in a specific way. This produces a characteristic spectrum of gravitational waves that differs from inflation. The waves should be strongest at high frequencies, opposite to inflation's predictions. Another prediction involves the axion field, a hypothetical particle related to the dilaton. In pre-Big Bang models, axions are produced abundantly during the bounce. These primordial axions could make up dark matter. The the mysterious invisible mass that dominates galaxy halos. Detecting relic axions from the pre-Big Bang phase would provide strong evidence for the model. The scenario also addresses cosmological puzzles differently than inflation. The uniformity of the cosmic microwave background arises because the pre-Big Bang universe had enormous time for regions to equilibrate. Millions of billions of years before the bounce, distant patches were in causal contact. They came to the same temperature naturally, with no inflation needed. However, pre-Big Bang cosmology faces serious challenges. The biggest is the singularity at the bounce point. Even though string theory smooths things out, detailed calculations show curvatures still become extremely large. Whether the bounce truly avoids a singularity depends on aspects of string theory that remain incompletely understood. There are also fine-tuning concerns. For the pre-Big Bang universe to evolve into our post-Big Bang universe with the right properties, initial conditions must be carefully chosen. The dilaton needs to start with specific values. The rate of contraction must fall within narrow ranges. Critics argue this trades one set of fine-tunings for another. Observational tests have been unkind to pre-Big Bang models. The predicted gravitational wave spectrum has not been detected. Measurements of the cosmic microwave background favor inflation over pre-Big Bang scenarios. The smoking gun signatures have not appeared, but absence of evidence is not evidence of absence. Future experiments with better sensitivity might reveal subtle signals. What pre-Big Bang cosmology contributed, regardless of whether it is correct, is imagination. It showed that string theory naturally contains mechanisms for extending cosmic history beyond the Bang. The theory that tries to explain fundamental particles also has things to say about the universe's origin. Strings vibrating in 10 dimensions might hold the key to what came before. What if time never started? What if the universe has always existed, stretching infinitely into the past, with no first moment? This idea violates intuition. Everything we experience has a beginning. Lives start at birth. Buildings start with foundations. Stories start with opening lines. Surely the universe must have started somewhere. But physics does not care about intuition. The equations do not require a beginning. In fact, several cosmological models suggest time is eternal in both directions. The universe has been around forever and will continue forever. The Big Bang was not the dawn of time. It was just an event in an infinite timeline. Alan Guth has been exploring this concept with cosmologist Sean Carroll. They are developing models where the universe exists at all times, extending infinitely into the past. The key insight is that the arrow of time, the direction from past to future, is defined by entropy. Entropy increases toward the future. Decreasing entropy defines the past. In their model, there is a special moment of minimum entropy. This low entropy point is what we call the Big Bang. On one side of this point, entropy increases in the usual way. This is our observable universe, evolving forward in time as galaxies form and stars die. But on the other side of the minimum, entropy also increases. Time flows in the opposite direction from our perspective. From an outside view, the universe is symmetric in time. There are two arrows pointing away from the low entropy moment in opposite temporal directions. Observers on either side experience increasing entropy and call that direction the future. They both think they are evolving away from the Big Bang. Each sees the other side as the past, but neither side is privileged. Neither is the true beginning. This time-symmetric cosmology has bizarre implications. The universe contains two regions, one before and one after the minimum entropy point. These regions have opposite arrows of time. If beings evolve on the other side, they would remember their Big Bang and anticipate our era as their future. We remember our Big Bang and anticipate their era as our past. Memory and causation work opposite ways across the divide. Does this mean there are actual beings living backwards in time? Probably not in any meaningful sense. The The time-reversed region likely has very different conditions than ours. But mathematically, the symmetry is exact. The laws of physics do not distinguish past from future at a fundamental level. Only the entropy gradient makes time asymmetric. Other models of eternal time use different mechanisms. Loop quantum cosmology with infinite bounces extends time infinitely into the past. Each bounce is separated by trillions of years. As you go back, you encounter bounce after bounce with no first bounce. The universe has always been bouncing. Conformal cyclic cosmology makes a similar claim. Penrose's cycles stretch to infinity in the past. There was no first eon. Each eon had a predecessor. The infinite regress never terminates. Our eon is one beat in an eternal rhythm with no starting downbeat. Eternal inflation also produces infinite time, in a sense. The inflating space has no beginning. Pocket universes bubble off endlessly, but the larger inflating background exists eternally. Our pocket universe is 13.8 billion years old. The multiverse containing it is infinitely old. Philosophically, time without a beginning challenges deep intuitions. Humans naturally ask, what came first? Where did it all start? These questions assume a first cause, a primordial event that set everything in motion. But maybe causation works differently at cosmic scales. Maybe causes and effects form an infinite chain with no ultimate first link. Mathematically, eternal time is perfectly acceptable. Infinities appear throughout physics without causing problems. The number line extends infinitely in both directions. Past and future times are just positions on this line. There is no reason mathematically to prefer a finite past over an infinite one. However, eternal time models still must explain features of our universe. Why is entropy so low at the Big Bang if time extends before it? An infinite past should have infinite opportunities for entropy to increase. The universe should be in thermal equilibrium, a boring state of maximum disorder. Yet we observe high order. This is called the Boltzmann brane problem. In an infinite past, random fluctuations would occasionally produce ordered states by chance. These fluctuations are far more likely to produce small ordered regions, like a single brain with false memories, than entire ordered universes. If time is eternal, you are more likely a Boltzmann brain with fake memories than a real person in a real universe. This paradox suggests either time is not truly eternal, or our understanding of probability in infinite systems is flawed. Physicists debate which resolution is correct. Some argue for a beginning after all. Others say the measure problem makes probability calculations meaningless in eternal models. The question remains open. Time might have started at the Big Bang, or time might stretch infinitely in both directions, with the Big Bang merely a special low-entropy moment in an eternal history. Current observations cannot distinguish between these possibilities. What is certain is that the more we learn, the less certain we become about time itself. In the 1960s, John Archibald Wheeler and Bryce DeWitt tried to quantize the universe. They wanted to apply quantum mechanics to cosmology, treating the entire universe as a quantum system. The result was an equation bearing both their names. This equation was supposed to describe the quantum state of the universe across all moments in time. But the Wheeler-DeWitt equation has a strange property. It contains no time variable. Time disappears from the equation entirely. This creates what physicists call the problem of time. How can you describe the evolution of the universe when the equation lacks any parameter representing when things happen? In ordinary quantum mechanics, Schrödinger's equation tells you how a wave function evolves over time. You start with an initial state and calculate what it becomes later. The time variable is explicit. The future follows from the past in a deterministic way. But the Wheeler-DeWitt equation eliminates this structure. All moments exist simultaneously in the equation. Past, present, and future are frozen together. This timelessness is not a bug. It comes from general relativity's core insight that time is relative. Different observers measure different time intervals depending on their motion and gravitational environment. There is no universal clock ticking the same for everyone. When you try to quantize such a theory, you lose even the notion of a preferred time direction. Despite this conceptual difficulty, physicists applied the Wheeler-DeWitt equation to cosmology. They modeled simple universes with specific symmetries to make calculations tractable. These toy models revealed something disturbing. The equation allowed quantum states that passed through singularities. The Big Bang singularity was not automatically resolved by quantization. In some solutions, the wave function representing the universe peaks at zero volume. The most probable state is a universe crushed to infinite density. This made no physical sense. If quantum mechanics could not eliminate singularities, what good was it? Loop quantum cosmology emerged partly as a response to this failure. Loop quantum gravity approaches quantization differently than the Wheeler-DeWitt equation. Instead of treating space as smooth, loop quantum gravity discretizes geometry into quantum chunks. This discreteness changes the structure of the quantum evolution equation. In loop quantum cosmology, the modified equation does eliminate singularities. The wave function never becomes large at zero volume. Instead, it peaks at some finite minimum volume determined by the Planck scale. The universe bounces rather than collapsing to a point. Loop quantization succeeded where the Wheeler-DeWitt approach failed. Why does loop quantum gravity work better? The Wheeler-DeWitt equation treats spatial geometry as continuous. It allows arbitrarily small volumes. But loop quantum gravity introduces a minimum quantum of volume. You cannot have less than one quantum. This built-in cutoff prevents densities from becoming infinite. Another advantage of loop quantum cosmology is that it restores a notion of time. Although time disappears from the fundamental equation, an effective time variable emerges from the quantum state's evolution. This effective time corresponds roughly to the volume of the universe. As volume changes, the quantum state evolves. Observers inside the universe experience this evolution as time passing. The Wheeler-DeWitt equation could not provide such an emergent time variable. The timelessness was fundamental and irreducible. Physicists struggled for decades to interpret what the solutions meant. How do you extract predictions about when things happen if the equation does not reference time? Some physicists embraced the timelessness. Julien Barbour argued that time is an illusion. The universe is really a vast collection of possible configurations, all existing simultaneously. What we experience as time is just motion through this configuration space. The Wheeler-DeWitt equation captures this timeless reality. Others found this interpretation unsatisfying. We experience time. Clocks tick. Causes precede effects. Any theory that cannot account for temporal experience seems disconnected from reality. The Wheeler-DeWitt equation's failure to resolve singularities and explain time suggested it was not the right approach. Modern quantum cosmology has largely moved beyond the Wheeler-DeWitt equation. Loop quantum cosmology, string theory, and other approaches provide alternative frameworks. Each handles time and singularities differently. None is complete or universally accepted, but all recognize that quantizing gravity is far more subtle than early researchers anticipated. The Wheeler-DeWitt equation remains important historically. It showed that combining quantum mechanics and general relativity creates deep conceptual puzzles. Time, which seems fundamental to both physics and experience, becomes ambiguous when you try to quantize the universe. Whether time is real or emergent, absolute or relative, remains one of the deepest questions in physics. The failure of the Wheeler-DeWitt equation taught physicists humility. Quantizing the universe is not a simple calculation. It requires rethinking the nature of reality itself. And whatever came before the Big Bang likely operates under rules we have not yet imagined. Zoom into the fabric of reality. Past atoms, past protons, past quarks. Keep zooming into smaller and smaller distances. Eventually, you reach a scale where space itself becomes grainy. This is the Planck length, about 10 to the power of minus 35 meters. It is 20 orders of magnitude smaller than a proton. At this scale, physics transforms completely. The smooth spacetime of general relativity dissolves into quantum foam. Virtual black holes pop in and out of existence. Cause and effect become fuzzy. Even the concepts of distance and duration lose clear meaning. This is Planck scale physics, where quantum mechanics and gravity merge into something we barely understand. Max Planck discovered this fundamental length in 1899 by combining fundamental constants. Take the speed of light, Newton's gravitational constant, and Planck's constant from quantum mechanics. Combine them in just the right way, and out pops a length scale. This length is not arbitrary. It represents the distance at which quantum gravitational effects become strong enough to dominate classical gravity. Why does this scale matter for cosmology? Because the singularity at the Big Bang supposedly compressed all of space to sub-Planck sizes. At such compression, our theories completely fail. General relativity predicts infinite curvature. Quantum mechanics predicts enormous fluctuations. Neither theory knows how to handle the other's effects. We are blind to what really happened. Quantum gravity theories attempt to describe Planck scale physics. String theory proposes that fundamental constituents are not points, but tiny strings, about 1 Planck length long. When objects get compressed to this size, the string nature becomes important. Strings resist being crushed smaller. They provide a natural cutoff, preventing infinite compression. Loop quantum gravity takes a different approach. It suggests space itself is made of discrete quantum units. The smallest possible area is about 1 Planck length squared. The smallest possible volume is about 1 Planck length cubed. You cannot divide space finer than these quanta. This discreteness prevents singularities from forming. At the Planck scale, energy densities reach the Planck density, about 10 to the power of 93 grams per cubic centimeter. This is the density where a region of space would collapse into a black hole if compressed further. The Planck density represents the maximum possible density of matter and energy. Beyond this point, conventional notions of matter break down entirely. The Planck time, about 10 to the power of minus 43 seconds, is how long it takes light to travel 1 Planck length. This is the shortest meaningful interval of time. Below the Planck time, quantum fluctuations in space-time geometry become so large that time itself becomes uncertain. You cannot measure durations shorter than this. The early universe crossed through Planck scale physics during the first instance after the Big Bang. Between 0 time and 1 Planck time, the universe was smaller than 1 Planck length. During this era, quantum gravity was in full control. Whatever happened then set the initial conditions for everything that followed. Unfortunately, we cannot build experiments that probe the Planck scale directly. The energies required are about 10 to the power of 19 times higher than the Large Hadron Collider can achieve. We cannot smash particles together hard enough to create Planck scale effects in the laboratory. We must rely on theory and indirect observations. Cosmology provides one way to test Planck scale physics. If quantum gravity processes during the Big Bang left observable imprints, we might detect them in the cosmic microwave background or in gravitational waves. These observations probe energy scales we cannot reach with particle accelerators. The universe itself becomes our laboratory. Loop quantum cosmology predicts specific deviations from standard cosmology caused by Planck scale effects. The bounce replaces the singularity. The expansion rate after the bounce depends on quantum geometry corrections. These corrections could show up as small anomalies in the distribution of galaxies or the spectrum of the cosmic microwave background. String theory makes different predictions. The extended nature of strings modifies short-distance physics. Black hole formation changes. Gravitational waves from the early universe might have unusual properties. Some string models predict extra dimensions could become detectable at energies approaching the Planck scale. The challenge is that Planck scale effects are extraordinarily subtle. They are largest right at the Big Bang, but that is precisely when physics is most uncertain. As the universe expands and cools, Planck scale corrections become smaller, and space and time merge with matter and energy in ways we can barely imagine. The rules of reality itself are written in this quantum foam, and whatever existed before the Big Bang must have navigated through this strange realm where normal physics ends and something more fundamental begins. Not all bounces are created equal. Loop quantum cosmology focuses on quantum gravity repulsion at the Planck scale. Ekpyrotic models invoke brane collisions in extra dimensions, but there is another class of bounce cosmologies that use matter itself as the bouncing agent. These are called matter bounce scenarios. The basic idea is simple. Imagine the universe contracting, filled with matter. As compression continues, the matter becomes denser and pressure increases. Eventually, pressure becomes so large it overcomes gravitational attraction. The matter rebounds, pushing the universe back into expansion. No quantum gravity needed, just extreme matter physics. For this to work, the matter must have unusual properties. Ordinary matter, like gas and dust, has positive pressure. Positive pressure actually increases gravitational attraction through Einstein's equations. If you want matter to create a bounce, you need negative pressure or some other exotic equation of state. One possibility is a scalar field with kinetic energy dominating over potential energy. Such a field can have negative pressure under the right conditions. As the field rolls in the contracting universe, its kinetic energy grows. This kinetic energy generates negative pressure that becomes very large at small volumes. When negative pressure is large enough, it drives the bounce. Another approach uses higher-order corrections to gravity. Einstein's general relativity is just the simplest theory of gravity. More complicated theories include extra terms involving higher powers of curvature. These terms are negligible at ordinary densities, but become important at extreme compression. They can modify gravitational attraction to be repulsive at high densities, causing a bounce. Matter bounce scenarios have several advantages. They do not require speculative new physics, like quantum gravity or extra dimensions. They work with known types of matter and well-studied modifications of gravity. The mathematics is more tractable than full quantum gravity. Predictions can be calculated with greater confidence. These models also address cosmological puzzles without inflation. The slow contraction before the bounce naturally produces a flat, uniform universe. Quantum fluctuations during contraction generate density perturbations with the right properties to match observations. The matter bounce provides a complete alternative to the inflationary paradigm. However, matter bounce scenarios face challenges. One is the anisotropy problem. If the contracting universe has any irregularities in its shape or expansion rate in different directions, these irregularities grow during contraction. By the time the universe reaches the bounce point, it could be wildly anisotropic, looking completely different in different directions. This conflicts with observations. Our universe appears highly isotropic. The cosmic microwave background looks nearly identical in every direction. If the universe bounced from an anisotropic contraction, it should carry visible imprints of that anisotropy. We do not see such imprints, which is a problem for many matter bounce models. Some researchers argue that the matter field's properties can suppress anisotropy growth. If the equation of state is carefully chosen, the field can stabilize the contraction against runaway anisotropies. But this requires fine-tuning the matter properties, which bothers physicists who prefer more robust mechanisms. Another challenge is the singularity. Just because matter generates large pressure does not guarantee a smooth bounce. Detailed calculations show that in some matter bounce models, space-time curvature still diverges at the transition point. a singularity forms, even though matter pressure opposes it. The matter cannot always overcome the singular behavior of Einstein's equations. To truly avoid singularities, matter bounce models often invoke quantum corrections. When densities approach the Planck scale, quantum effects modify the effective pressure and energy density. These quantum corrections can ensure the bounce is smooth. But now you have reintroduced quantum gravity through the back door. The model is no longer purely classical. Despite these issues, matter bounce scenarios remain actively researched. They offer a different perspective on how universes might avoid singularities and cycle through phases. The physics is less exotic than branes or quantum geometry, making the predictions easier to test against observations. One attractive feature is the connection to dark energy. The same scalar field that drives the bounce could be responsible for the current accelerated expansion. Dark energy might be this field in a different regime. This unifies the explanation for the early universe bounce and the late universe acceleration using a single ingredient. Future observations will constrain matter bounce models. The spectrum of primordial gravitational waves differs from inflation and from other bounce mechanisms. Precision measurements of the cosmic microwave background polarization could distinguish between scenarios. The distribution of matter on the largest scales also carries signatures of the pre-bounce dynamics. Matter bounce cosmology shows that multiple paths lead away from the singularity problem. Whether the universe bounced due to quantum gravity, colliding branes, or exotic matter properties remains unclear. But the bouncing universe paradigm has moved from speculation to serious scientific investigation. The Big Bang might be a cosmic rebirth, with matter itself providing the midwife that delivered our expanding universe from the contracting womb that preceded it. 70% of the universe is made of something invisible, something that pushes space apart faster and faster. Astronomers discovered this dark energy in 1998 by observing distant exploding stars. The explosions appeared dimmer than expected, revealing that cosmic expansion is accelerating. Something is counteracting gravity on the largest scales. Dark energy seems like a modern problem, but it might hold the key to what came before the Big Bang. In cyclic cosmologies, dark energy is not just causing our current acceleration, it is preparing the universe for its next phase. The force that pushes galaxies apart now could be the same force that enables the next cosmic cycle. In the cyclic ekpyrotic model, dark energy represents the attractive force between branes in the extra dimension. Right now, the branes are being pushed apart, appearing to us as accelerated expansion. But this force is actually pulling the branes through the bulk toward their next collision. What looks like repulsion in three-dimensional space is attraction in the higher dimensional space. Eventually, the attractive force will dominate completely. The universe will stop expanding and begin contracting. This contraction phase could last trillions of years, slowly bringing the branes back together. The cycle that began with their last collision will end with their next collision. Dark energy is the engine driving this eternal repetition. This interpretation makes dark energy purposeful rather than mysterious. It is not a random cosmological constant that happened to be incredibly small for no reason. It is a dynamical field with a specific role in cosmic evolution. The field's current value and behavior are determined by where we are in the cosmic cycle. Other cyclic models use different mechanisms, but share the idea that dark energy is cyclical. In Penrose's conformal cyclic cosmology, dark energy causes the universe to expand to enormous size and low density. This far future state then transitions into the next Big Bang. Dark energy creates the conditions necessary for the transition between aeons. Loop quantum cosmology can incorporate dark energy as a field that drives expansion after the bounce. The same field might have existed before the bounce, causing contraction. During the bounce, quantum gravity effects reverse the field's role, transforming contraction into expansion. Dark energy oscillates between driving collapse and driving acceleration across cosmic cycles. If dark energy is part of a cyclic mechanism, we can make predictions. The acceleration rate should not be exactly constant. It should change slowly over time, in ways determined by the cycle's dynamics. Current observations suggest acceleration is constant within measurement errors, but future more precise measurements might detect subtle variations that reveal dark energy's true dynamical nature. Another prediction is that dark energy should have a specific relationship to other cosmological parameters. The cycle's total duration, the matter content of the universe, and the dark energy density should all be linked. Finding these correlations would support cyclic models over models where dark energy is just a random constant. Dark energy also affects the universe's ultimate fate. In standard cosmology, with a constant dark energy, the universe expands forever. Galaxies separate beyond each other's horizons. Stars exhaust their fuel. Black holes evaporate. Eventually, only isolated particles remain in an exponentially expanding void. This is the heat death scenario, a cold, empty future with no possibility of new structure. But if dark energy is cyclic, heat death is avoided. Before the universe becomes completely cold and empty, the cycle reverses. Contraction begins. The universe heats up again. New structures can form in the next cycle. The cosmos avoids eternal stagnation by periodically refreshing itself. This raises questions about entropy. The second law of thermodynamics states entropy always increases. Each cycle should be more disordered than the last. How can the universe keep cycling indefinitely if disorder constantly accumulates? Some cyclic models propose that the universe grows slightly larger with each cycle. The extra volume provides more phase space for entropy to spread into. Entropy increases in absolute terms, but decreases relative to the available volume. This allows cycles to continue without violating thermodynamics. Others suggest black holes reset entropy during the transition. Black holes have enormous entropy. When they evaporate at the end of a cycle, they release that entropy as radiation. The radiation then gets recycled into the next cycle in a way that produces low entropy initial conditions. The details remain speculative. What is clear is that dark energy is central to understanding cosmic history. It is not just affecting our current era, it connects past, present, and future. The force accelerating galaxies today might be the descendant of whatever ended the previous universe and the ancestor of whatever will end ours. Dark energy is not the mysterious afterthought it appears to be in standard cosmology. It might be the conductor orchestrating the universe's eternal symphony. When matter falls into a black hole, it seems to disappear forever. The event horizon marks a point of no return. Anything crossing that boundary can never escape. For decades, physicists believed information was destroyed in black holes. This violated quantum mechanics, which says information is always preserved. The contradiction created the black hole information paradox. Stephen Hawking eventually argued that information does escape, encoded in the subtle quantum correlations of Hawking radiation, but the escape process takes astronomical time. For a black hole with the mass of billions of stars, complete evaporation requires 10 to the power of 100 years. By then, the universe has evolved unimaginably far from its current state. Now consider a cyclic universe. At the end of each cycle, all matter has either decayed or fallen into black holes. Those black holes gradually evaporate, releasing their contents as radiation. If information survives this process, then knowledge about the previous universe could pass into the next one through the radiation. In Penrose's conformal cyclic cosmology, this information transfer is central. The final evaporation of black holes creates Hawking points in the next universe. These points carry information about the mass and spin of the original black holes. An observer studying Hawking points in the cosmic microwave background could potentially reconstruct properties of black holes from the previous aeon. This creates a form of cosmic inheritance. Each cycle does not start from scratch with completely random initial conditions. It inherits structure from its predecessor. The largest black holes from one eon become the seeds of structure in the next. Information flows across the boundary between cycles. But how much information survives? Hawking radiation is nearly thermal, meaning it looks almost completely random. Extracting information from thermal radiation is extraordinarily difficult. It is like trying to read a book after it has been burned and the ashes scattered. The information might technically survive, but it is practically inaccessible. Recent work in quantum gravity suggests more information survives than previously thought. Calculations using the holographic principle show that black hole radiation contains subtle correlations. These correlations encode everything that fell into the black hole, though deciphering them requires knowing the black hole's exact quantum state. Loop quantum cosmology offers a different mechanism for information transfer. The quantum bridge, connecting, contracting, and expanding phases, allows quantum states to pass through. Scalar fields, representing matter, carry information continuously across the bounds. The transition is smooth enough that some properties survive intact. String theory provides yet another possibility. In some string models, black holes are not truly singular. Their interiors contain exotic geometries involving extra dimensions. Matter falling into these geometries might be stored rather than destroyed. When the black hole evaporates, the stored information gets released. If black holes persist through cosmic cycles, they could carry information from one cycle to the next. Why does information survival matter? Because it connects the fate of our universe to the origin of the next. If information is destroyed at cycle boundaries, each universe is independent. But if information survives, there is continuity across cycles. The multiverse becomes less fragmented. Cause and effect can span cosmic epochs. This has philosophical implications. If your brain state's information persists through cycles, could you be reconstituted in a later universe? Not exactly, since the thermal scrambling would disperse your information across space. But the raw data, describing your neural connections, would still exist somewhere in the next cycle's radiation bar. More practically, information survival affects predictions. In models where information is lost, the next cycle starts with random initial conditions. You cannot predict much beyond statistical averages. But if information survives, the next cycle's properties depend on the previous cycle's properties. Correlations exist across cycles that could be tested observationally. Current observations cannot yet detect information transfer between cycles. The signals are too weak and too degraded by the violent processes at cycle transitions. But future gravitational wave detectors might catch hints. Peculiar correlations in the gravitational wave background could indicate information leaking through from a previous universe. Black holes are not just cosmic garbage disposals. They are information processing systems that might preserve knowledge across the ultimate boundary. The material of one universe could become the initial conditions of the next, with black holes serving as cosmic filing cabinets. What falls into darkness might not be lost forever. It might simply be waiting for the next beginning. The cosmic microwave background looks nearly identical in every direction. Temperature varies by only 1 part in 100,000 across the entire sky. This remarkable uniformity created a major puzzle for cosmology. Regions on opposite sides of the sky have never been in causal contact. They are too far apart for light to have traveled between them in the universe's lifetime. How did they end up at the same temperature? This is the horizon problem. Causally disconnected regions should have independent temperatures. They never had time to equilibrate. Yet they are identical to extraordinary precision. In standard Big Bang cosmology, this coincidence seems miraculous. About 100,000 independent regions somehow started with nearly identical properties for no apparent reason. Cosmic inflation solves this problem by making the observable universe originate from a tiny region that was in causal contact. Before inflation, this region had time to equilibrate. Then, inflation stretched it to enormous size. carrying the uniformity to scales larger than the causal horizon. Different parts of the sky were once neighbors. They only appeared disconnected because inflation expanded space faster than light could traverse it. But cyclic cosmologies solve the horizon problem without inflation. The key is the contracting phase before the bounce. During contraction, the horizon grows rather than shrinks. Regions that are causally disconnected in the expanding phase were connected in the contracting phase. They equilibrated back then. Think about what happens as the universe contracts. Light cones that are separated now converge as you trace them backward in time. Eventually, they overlap. Information could travel between what are now distant regions. They had ample time to come to the same temperature during the long, slow contraction leading up to the bounce. When the universe bounces and begins expanding, this inherited uniformity is preserved. The post-bounce expansion takes initially uniform conditions and maintains them. No period of accelerated expansion is needed. The contracting phase naturally sets up the uniform initial state that inflation was invented to create. This solution is more economical than inflation in some ways. It does not require a new field, the inflaton, with carefully tuned properties. It does not need a special period of exponential expansion. The standard physics of contraction and expansion suffices. Simplicity favors the cyclic explanation. However, critics point out complications. During contraction, instabilities can grow. Small perturbations in the density or geometry can become large. If the pre-bounce universe had any irregularities, they might amplify rather than smooth out. The contracting universe could become chaotic and anisotropic before reaching the bounce. Cyclic model proponents argue that specific types of contraction avoid these instabilities. A slowly contracting phase, dominated by a scalar field, can remain smooth. The field's energy density grows slowly enough that perturbations do not run away. The mathematics shows this is possible, though it requires the scalar field to have particular properties. Another advantage of cyclic models is explaining the flatness problem. The universe's spatial geometry is extraordinarily close to flat. In standard cosmology, flatness is unstable. Any deviation from perfect flatness grows over time. For the universe to be as flat as observed today, it must have been unbelievably flat at the Big Bang. Why? Inflation stretches space so much that even a curved geometry looks flat afterward. But cyclic cosmology achieves flatness differently. The contracting phase naturally drives the geometry toward flatness. As space contracts, curvature smooths out. By the time the bounce occurs, the universe is flat to high precision. The expansion after the bounce preserves this flatness. So cyclic models solve both the horizon and flatness problems using the same mechanism, a contracting phase before the bounce. This is elegant. One dynamical process addresses multiple puzzles. Inflation requires fine-tuning to start correctly and produces a multiverse as a side effect. Cyclic models avoid both issues. The debate between inflation and cyclic cosmology often focuses on predictions. Both models match current observations well. The cosmic microwave background looks the same, whether it came from inflation or a pre-bounce contracting phase. To distinguish between them requires more precise measurements. One key difference is gravitational waves. Inflation produces a specific spectrum of primordial gravitational waves. These waves arise from quantum fluctuations during the accelerated expansion. The amplitude depends on the energy scale of inflation. Most cyclic models predict much weaker gravitational wave signals. The contracting phase does not amplify quantum fluctuations the way inflation does. Future gravitational wave observatories might detect the primordial background. If they find strong signals matching inflationary predictions, cyclic models are challenged. If they find weak signals or none at all, cyclic models gain support. The stakes are high. Observations could definitively rule out one class of theories. The horizon problem reveals how observations constrain theories about the pre-bang universe. The cosmic microwave background's uniformity is a clue. Whether that clue points to inflation or to a previous contracting phase remains an open question. But one thing is clear: the universe's smoothness demands explanation, and that explanation might require looking backward past the Big Bang itself. Gravitational waves are ripples in space-time itself. When massive objects like black holes or neutron stars collide, they shake the fabric of space, sending waves outward at light speed. Detectors like LIGO caught these waves from violent cosmic events. But there might be another type of gravitational wave, far older and weaker, created in the first instance after the Big Bang. These primordial gravitational waves are fossils from the universe's birth. They were produced by quantum fluctuations when the universe was unimaginably small and hot. As space expanded, the waves stretched to enormous wavelengths. Today, they would appear as extremely faint ripples pervading all of space, a background hum from the beginning of time. Different theories of the early universe predict different gravitational wave signatures. This makes primordial waves a powerful tool for testing what came before the Big Bang. Inflation, bouncing cosmologies, and cyclic models each produce distinct patterns. Measuring these patterns could definitively distinguish between scenarios. Inflation generates gravitational waves through a specific mechanism. During the exponential expansion, quantum jitter in the gravitational field gets amplified. These fluctuations become classical gravitational waves. The amplitude depends on how fast space expanded. Higher energy inflation produces stronger waves. The spectrum is nearly scale invariant, meaning waves of different wavelengths have similar amplitudes. This predicted spectrum has a characteristic shape. Physicists call it the tensor power spectrum. The word tensor refers to the mathematical description of gravitational waves. If inflation occurred at high energies, about 10 to the power of 16 giga-electron-volts, the tensor power spectrum should be large enough to detect with current or near-future experiments. Cyclic cosmologies predict much weaker gravitational waves. During the contracting phase before the bounce, gravitational perturbations behave differently than during inflation. They do not get amplified as much. The bounce itself might produce some waves, but the amplitude is smaller than inflation predicts. The spectrum also has a different shape, with more power at small scales than large scales. Loop quantum cosmology makes specific predictions about bounce-generated waves. As the universe passes through minimum volume, quantum geometry effects create a burst of gravitational radiation. The frequency and amplitude depend on details of the loop quantization. Some calculations suggest the waves would be too weak to detect. Others find marginally detectable signals in the frequency range future space-based detectors will probe. Ekpyrotic models predict extremely weak gravitational waves from the pre-bounce phase. The slow contraction does not amplify quantum fluctuations. Only density perturbations get enhanced. If ekpyrotic cosmology is correct, primordial gravitational wave searches will come up empty. This makes the theory falsifiable. Strong detections would rule it out. String theory scenarios have diverse predictions depending on which string model you consider. Pre-Big Bang string cosmology predicts a unique gravitational wave spectrum with most power at high frequencies. These waves would be produced during the dilaton-driven contraction phase. They differ from both inflation and standard bounces. How do we detect primordial gravitational waves? They leave imprints on the cosmic microwave background. The waves create a specific polarization pattern in the ancient light. This pattern is called B-mode polarization. Detecting B-modes would be the first evidence of primordial gravitational waves. Several experiments have searched for B-modes. The BICEP 2 telescope claimed detection in 2014, causing enormous excitement. If true, it would confirm inflation and rule out many alternatives. But further analysis showed the signal came from dust in our galaxy, not from primordial waves. The search continues with improved experiments. Even if B-modes are detected, distinguishing between theories requires measuring the spectrum precisely. Inflation and bounces might produce similar overall amplitudes but different frequency dependencies. Observations across multiple frequency ranges would map the full spectrum. Comparing measurements to predictions would reveal which theory is correct. Space-based gravitational wave detectors like LISA will open new windows. These detectors are sensitive to lower frequency waves than ground-based instruments. They could catch gravitational waves from early universe processes that LIGO cannot see. If primordial waves exist in LISA's frequency range, they would be detected within years of operation. Pulsar timing arrays offer another detection method. Pulsars are rapidly rotating neutron stars that emit regular radio pulses. Gravitational waves, passing between Earth and a pulsar, alter the pulse arrival times. By monitoring many pulsars for years, astronomers can detect extremely long wavelength gravitational waves. This technique is sensitive to waves produced by different early universe mechanisms than those accessible to LIGO or LISA. The next decade will be decisive. Multiple experiments are coming online with sufficient sensitivity to detect primordial waves if they exist at predicted levels. Positive detections would revolutionize cosmology. Null results would rule out high-energy inflation and support alternative scenarios. Gravitational waves carry information from epochs we can never see with light. They pass through matter unimpeded, preserving their primordial properties. Measuring them is like opening a sealed message from the universe's first moments. That message might reveal whether the Big Bang truly was a beginning or just another transition in an eternal cosmic story. Imagine counting to infinity. You start with 1, then 2, then 3. You keep going forever, never stopping. After an infinite amount of time, have you reached infinity? The question seems nonsensical. Infinity is not a destination. It is a process without end. This confusion illustrates the measure problem, one of the deepest challenges facing multiverse cosmology. In eternal inflation, the universe contains infinite regions. Each region can have different properties. Some regions have one value of the cosmological constant. Others have different values. In principle, every possible value occurs infinitely many times, somewhere in the infinite multiverse. So, how do you calculate probabilities? Normally, probability means counting favorable outcomes divided by total outcomes. If there are 6 sides on a die and one favorable outcome, the probability is 1/6. But what if there are infinite favorable outcomes and infinite total outcomes? You get infinity divided by infinity, which is undefined. Mathematics breaks down. This is the measure problem. You cannot assign meaningful probabilities in an infinite multiverse using naive counting. Different ways of counting give different answers. The predictions depend on how you order your counting procedure, which seems arbitrary. Theories that predict everything are actually predicting nothing. Alan Guth calls this the youngness paradox. If the multiverse has existed eternally and continues producing pocket universes forever, most observers should live in extremely young universes. The vast majority of intelligent beings would exist shortly after their pocket universe formed. We should observe ourselves in a barely evolved cosmos, not a 13.8 billion-year-old universe with mature galaxies. But we do not observe that. Our universe is middle-aged by cosmic standards. Stars have gone through multiple generations. Heavy elements are abundant. Life had time to evolve. This seems incompatible with eternal inflation if you count all observers equally. To escape the paradox, cosmologists introduce cutoff procedures. Instead of counting all pocket universes produced over infinite time, count only those produced within a finite space-time volume, or weight different regions by some physical quantity like entropy. These cutoffs make probability calculations well-defined again. However, different cutoff procedures give different predictions. There is no unique way to regulate the infinities. Raphael Bousso proposed one sophisticated cutoff called the causal diamond measure. It counts only observers within the past and future light cones of a given space-time point. This method has nice properties, and makes certain predictions about cosmological parameters. Other physicists prefer different measures. Some argue we should count regions weighted by entropy. Others propose counting quantum branches weighted by their amplitude. Each measure changes the predictions about what we should observe. The theory becomes ambiguous when infinities are involved. Cyclic cosmologies claim to avoid the measure problem by not having an infinite multiverse. There is one universe going through cycles. Even if the number of cycles is infinite, observers in any given cycle are finite. You can meaningfully ask what typical observers should see without dealing with the comparison of infinities. But cyclic models have their own measure issues. If there are infinitely many cycles stretching into the past, which cycle are we in? Should we be in an early cycle or a late one? If properties change slightly between cycles, we need a probability distribution over possible cycles. This reintroduces ambiguity. Some physicists argue the measure problem indicates multiverse theories are not scientific. Science requires testable predictions. If a theory predicts everything with some probability, it cannot be falsified. Any observation is compatible with the theory. Karl Popper would reject such theories as metaphysical rather than scientific. Defenders respond that the measure problem is a technical challenge, not a fatal flaw. Many problems in physics seemed intractable until the right mathematical framework was discovered. Quantum mechanics once had severe conceptual problems that were eventually resolved. Perhaps a future understanding of quantum gravity will reveal the natural measure. The measure problem also appears in quantum mechanics through the many worlds interpretation. If every quantum measurement creates branching universes, you have infinite copies of observers across the branches. Calculating the probability of being in one branch versus another requires defining a measure over branches. Quantum mechanics faces analogous issues to eternal inflation. Despite the difficulties, some cosmologists embrace the measure problem as revealing something deep. Maybe probabilities are fundamentally ambiguous in infinite systems. Maybe physics cannot predict everything precisely. Our theories might give ranges of likely outcomes rather than definite predictions. This would be a profound shift in how science operates. For now, the measure problem remains unsolved. It is one reason many physicists resist multiverse theories, despite theoretical motivations for them. Without a clear way to make predictions, the theories lose explanatory power. They become consistent mathematical structures without empirical content. The measure problem shows that infinity is dangerous in physics. Infinite space-time volume, infinite numbers of universes, infinite cycles into the past, all create mathematical and conceptual tangles. Perhaps the true theory will avoid infinities entirely, or perhaps we need new mathematics to handle them properly. Either way, before we can understand what came before the Big Bang, we need to understand how to count. Theories about what existed before the Big Bang are not mere philosophy. They make predictions that future observations could test. The next generation of telescopes, gravitational wave detectors, and particle physics experiments will probe the universe's earliest moments with unprecedented precision. These observations might finally reveal whether the Big Bang was truly a beginning or just a phase transition. The most direct test involves the cosmic microwave background. This ancient light carries information from 380,000 years after the Big Bang, the earliest electromagnetic radiation we can observe. Subtle patterns in its temperature and polarization encode details about the pre-bang dynamics. If conformal cyclic cosmology is correct, Hawking points should appear as specific types of hotspots. Better maps of the microwave background with higher angular resolution might confirm or rule out these signatures. The European Space Agency's Planck satellite provided the best data so far. Future missions with even greater sensitivity could detect signals Planck missed. Loop quantum cosmology predicts slight deviations in the microwave background's power spectrum. The bounce modifies the amplitude of temperature fluctuations at certain scales. These modifications depend on quantum geometry parameters. Measuring the spectrum precisely enough to detect deviations would confirm that quantum gravity effects were important in the early universe. Gravitational waves provide another crucial test. Different pre-Bang scenarios predict vastly different primordial gravitational wave spectra. Inflation produces relatively strong waves. Ekpyrotic models produce extremely weak ones. Loop quantum bounces produce moderate signals with specific frequency dependencies. Detecting or not detecting these waves rules out entire classes of theories. Several experiments are underway. Ground-based cosmic microwave background telescopes look for B-mode polarization caused by gravitational waves. Space-based detectors, like LISA, will directly measure gravitational waves at frequencies inaccessible from Earth. Pulsar timing arrays monitor slight timing variations caused by passing waves. Together, these experiments cover a wide range of frequencies and sensitivities. If any experiment detects primordial gravitational waves with high confidence, we learn about the energy scale of the early universe. The wave amplitude tells us how violently space was fluctuating. Strong waves favor high-energy inflation. Weak or absent waves favor cyclic models or low-energy alternatives. The spectrum's shape distinguishes between different mechanisms. Particle physics experiments might also provide clues. If the universe went through a bounce rather than starting from a singularity, the laws of physics at the bounce point might differ from standard models. Exotic particles produced during the bounce could survive to today as dark matter. Detecting such particles in underground detectors or at colliders would support bounce cosmologies. The Large Hadron Collider already ruled out some predictions of pre-Big Bang models. Certain string theory scenarios predicted supersymmetric particles at energies the LHC can reach. None were found. This constrains string-based cyclic models. Future higher energy colliders will probe even more of the parameter space where new physics might hide. Observations of the universe's large-scale structure could reveal pre-Bang signatures. The distribution of galaxies across cosmic scales reflects the spectrum of primordial density fluctuations. Different early universe scenarios produce slightly different distributions. Galaxy surveys, mapping billions of galaxies, can detect these subtle differences. The Vera Rubin Observatory, currently under construction, will survey the southern sky every few nights for 10 years. It will map the positions and properties of billions of galaxies. Statistical analysis of this data will test cosmological models with unprecedented precision. If cyclic models predict correlations that standard inflation does not, the survey will find them or rule them out. Black hole observations might provide tests. If primordial black holes were produced in large numbers during a bounce or cyclic transition, they could make up some or all of dark matter. Gravitational lensing surveys and gravitational wave detections are already constraining the abundance of primordial black holes. Discovering them at specific mass scales would support scenarios where the early universe went through extreme densities. Neutrino astronomy is beginning to probe the high-energy universe. Cosmic neutrinos from the early universe would carry information about temperatures and densities that electromagnetic radiation cannot access. Detecting a cosmic neutrino background would open a new window on the first seconds after the bang. Deviations from standard predictions might indicate pre-bang physics. Ultimately, the question of what came before requires looking at converging lines of evidence. No single observation will definitively prove a theory, but if multiple independent measurements consistently favor one scenario over others, confidence builds. If gravitational waves, microwave background patterns, galaxy distributions, and particle physics observations all point the same direction, the case becomes compelling. The next 20 years will likely settle the question. Current experiments have the sensitivity to detect predicted signals if they exist. Future upgrades will push even further. By mid-century, cosmology might finally know whether the Big Bang was the beginning of time or merely one event in an eternal cosmic history. We stand at the threshold. The telescopes are being built. The detectors are coming online. The universe is about to tell us its oldest secret. All we have to do is listen.